data points, so we can just actually go down the center, right? And if we cut 15 and a half, right? We get 7.5, right? So if we go to the 8th data point, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's our midpoint. Agreed? That's where we were yesterday. And then I said that in this method, you basically, you then take each half and you bust it in half. And then I asked you guys to take a look into whether or not you thought, let's say when we go to the lower half, and we break that in half, we discard these outer sevens, or we include one in the lower half, one in the upper half? What do you think? What do you got? Anybody? Well, let me put it to you this way. Let's say instead of 3 sevens in the middle, let's say there were 5 sevens. So let's say one more here. Let's say you have that guy there, that guy there, and let's say that guy there. And all of the other data points being the same. What would you feel about the spread of all of the data? Would it be tighter or?
Tighter, I think.
It would be tighter, right? Because you're adding more information that's sitting around the center. So from my perspective, so if we were to discard these 2 outer sevens, that would mean that we would have to discard these 4, right? If we follow that same logic. In which case you would get the exact same diagram, wouldn't you? In both cases. So there would be no way to distinguish based on that logic between that case and that case. Make sense, Milad? You following what I'm saying?
I follow what you're saying, but it doesn't make sense.
Well, you follow what I'm saying, but it doesn't make sense. You want to go ahead and explain?
I think we should include this level.
That's what I'm doing.
No, you're discarding this.
No, that's not what I'm saying. I'm saying I'm going to include the 7, so you don't understand what I'm saying.
Yeah.
So, back to what I'm saying. If we were to discard the 7s, then case 1 and case 2 would yield the exact same result. But they are different scenarios. And clearly case 2, with these added couple of 7s, has more information clumped around the center, right? And if you discarded the 7s in both cases, the outer 7s, in case 1 you discard these 2, in case 2 you discard these 4, you wouldn't be able to tell the difference in terms of the result. So I say to keep them in. So if we keep them in, then the question is finding the midpoint of the lower half and the upper half. So now you have 1, 2, 3, 4, 5, 6, 7 data points, right? The only thing is, I'm wondering if when we find that middle, do we go relative to there or do we go relative to there? You guys have to double check that. Are we going relative to the edge of the middle, or are we just taking a look at the lower half of the data? I think we're just taking a look at the lower half. Well, why don't you guys check the textbook for that while I deal with this? Yeah. Coming back in yet? So, do I grab the lower half of this, or do I include that in my information? I think we just take this myself. And there are 7 data points. Well, you guys look, I'll do this. 1, 2, 3, 4. You guys want to check that? And while you check it, I'll just keep going based on feel, and then we'll come to some kind of agreement. You guys want to stop this right now? Can we stop it? What do I push? Or a median? we have a lower half of data, which I've circled over here. We want to find the midpoint of that lower half of the data. You can see that you have 3, 4, 5, 6, 7 data points. Your fourth data point is going to represent the median of the lower half of data. Your fourth data point to the right of the actual median is going to represent the median of the upper half of the data. And now you see you've broken it up into 4 parts, okay? Or 4 quarters. And that's why they use the letter Q, okay? To say that this represents the first quartile, second quartile, third quartile. And actually, there are 4 quartiles. So do they actually label the, yeah, they only label them Q1, Q2, Q3, Q1, Q2, Q3 as I've shown. And that's fine. So this is your first quarter of the data, your second quarter of the data, your third quarter of the data, and your fourth quarter of the data. Okay, so they call this thing a box and whisker plot. So the box is going to be running on the left edge from Q1 to Q3. With a line in the middle, well, not necessarily in the middle, a line in between Q1, Q3 of that box. Ideally, it's proportionally, but this is a sketch, leaning towards the closer of Q1 and Q3. In this case, the median, or Q2, is 2 away from Q1. It's 1 away from Q3, so maybe we'll draw the median instead of down the middle. We'll shift it a little bit down here. Does that make sense? What was Q1 equal to? 5. Q2? 3. And then the idea is to draw the whiskers. And I guess you want to somewhat keep things proportional, although you know what, when we're coming to tests and we're just doing sketches, it's not such a big deal. So we're going down to a half. I'm not going to force you to be proportional with that. I'm not going to hold you to that. Here we're going down quite a bit. We're going down from 5, we're going down 4.5. Here we're only going up 1, so maybe you, if you like, you can make that a little bit longer. And that data point is going to be 0.5. And this one you could make, I guess, a little bit shorter. And you can represent that as a 10. Okay? Are you guys clear on that? So I made it a part A and a part B, if I'm not mistaken, right? Did I do this part A, part B, or part 1, part 2 in the question? Anybody have their notes from last class? The question I made up? At any rate, let's assume that this was part A. This is your box and whisker plot. Then I asked about the modified box and whisker plot. Again, it's a definitional thing, and it's a modification of this based on a predetermined standard which tells you whether or not some of your data should be considered a quote-unquote outlier. And the standard is based on a width of 1.5 times this. The width of this box is called the interquartile range. And it makes sense because those are the central quarters, if you will, right? Here you have your outer quarters, right? Here you have your inner quarters, these two. So from here to here, this is your interquartile range. And if I'm not mistaken, the definition for a modified box and whisker plot is to say that any data points to the left of Q1 or data points to the right of Q3 that are more than 1.5 times this distance away from either edge get broken off of the whisker and get turned into a dot. And then the next closest one becomes the new whisker. So what do I mean by that? In this case, our interquartile range is, what is that, 8? Sorry, I'm not wearing a contact this morning. I can't wear it this morning. So our interquartile range is 3, correct? And based on their definition, we take 1.5 times that amount, which gives us 4.5. Agreed? So now what we simply have to do is we have to see if there are any data points a distance of 4.5 further than this right edge, and if there are, we take them out of this line and make them outliers. And if there are any 4.5 below that edge. Well, if you take a look at Q3 and you add 4.5 to it, that's 8, right? That gives you 12.5. Okay? But we don't have any data points that are greater than 12.5, right? So we don't touch that. And I don't think we're going to end up touching that either. And on the left side, if you take a look at Q1 minus 4.5, you have 5 minus 4.5, which gives you 0.5. This guy just makes it, right? Just makes it. So in this particular case, no difference, right? But let's say, for argument's sake, that that data point over there was not 0.5. Let's say it was 0.25. Okay? Let's say, for argument's sake, that that data point was 0.25. Who can tell me how this would change? Yes?
You put a dot at that point, and then you get the next number and the rest.
So if this data point was 0.25, 0.25 would have been more than a distance of 4.5 away from that left edge going left. So Milad says that, based on the definition, their definition of a modified box and whisker plot, becomes an outlier. Okay? And what becomes the left-hand whisker? The next data point. Now let's say you would have had 0.25 and 0.3 and then a 3. Well, then you would have had a couple of outliers, right? You can have more than one outlier, right? Based on that criteria. So, of course, yeah, that would, based on what we just said, that would be a 0.25, and then that would have been a 3, right? If indeed this was 0.25. Agreed? So if that was the case, you would have seen a difference between the modified box and whisker plot and the box and whisker plot. In our particular case, the way I made things, there's no difference. Okay, is that clear? Pretty straightforward stuff. And as I said, to me, the relevance of that, from what I've seen, could have to do with, say, two variable statistics, whereby each of the data points, let's say in a relation that you gather, are not absolute, that there's variation associated with each of those data points. So as I said, you could show, as I said last class, you could show a graph without dots, but dots could be represented as box and whiskers, right? Gives macro information and micro information to the reader. Okay, any, you guys follow that? You guys pretty clear on that? Yeah.
Where'd you get the 0.5, 3 times 1.5?
So their definition, if you actually take a look at it, says that a modified box and whisker plot is often used when the data contains outliers. By convention, so they've decided this. Statisticians have decided this. Any point that is at least, at least 1.5 times the box length away from the box is classified as an outlier. So if we actually say, if they're saying at least, they didn't say greater than, they actually said at least. So you know what? at least means this or this. So technically, this answer is not correct. I thought it was greater than a distance of, but they're saying at least. So guess what? Guess what I have to do to this?
Make a dot.
Make it a dot,
The next number is 1.
which is, what's our next number?
3.
So I'm actually glad that you asked that question there. You guys see in the book it says at least? So if you actually hit the cutoff, if you actually do hit the cutoff based on their definition in the book, this becomes an outlier. So that would be, so this is not true. This is not true. This is true. Are there any questions on that modification that I just made? Okay, it's a definitional thing. We're going based on a definitional thing here. We're not going based on anything else. It's not a logic thing. Just reading a book and assuming that that is the correct statistical definition of this particular thing. Okay, Eric, are you clear on that? Oh, so you understand where, you don't know where I got the 3, right?
No, the 1.5.
The 1.5?
Yeah.
Oh, that's right in the definition as well.
Oh.
It says, by convention, any point that is at least 1.5 times the box length away from the box. So the box length is from here to here, right?
Right.
So that gap is 3, you multiply it by 1.5, that's 4.5. Anything that is a distance of 4.5 or beyond on the right, from 8, or 4.5 that way, from 5 and beyond, is going to be turned into a dot. And where the dot represents an outlier. Yes?
So why is it 1.5?
No idea. No idea why they came up with that convention. You can make your own Milad, box, and whisker definition and make it 1.7.
But there should be a logic behind it.
Maybe. I have no idea. No clue. I think that one thing I can say about it is they want to come up with some kind of a convention. So there's got to be. You could have made it at 1.7, and there would be value to that as well. But one thing that would be stupid is if the people in one country are using 1.7 and people in another country are using 1.5, 1.3, and so on and so forth. So as long as everybody is consistent, then when you're looking at a research paper from wherever, you know that it's 1.5, then you can always work that back in your mind. Yeah.
What's the use of this box and whisker?
I just showed you before.
No, like,
So if you're looking, so for example, if you're looking at, were you not here yesterday? Were you paying attention?
what's here?
Were you paying attention?
Yes.
When I showed the 2 variable statistics
Yes.
plot? So you can show you, I can show you the data point, the data like this. Or I could represent each data point as a box and whisker plot. Some will not have a whisker, by the way. Sometimes you don't even have a whisker, and so on and so forth. So each data point could be arrived at through a bunch of information, which may have a tight or narrow spread associated with it. So if I'm looking at this graph, I can see the overall trend, and I can also see what kind of variation there is associated with each of the data points, right? And it's a visual thing. Obviously, it's a visual thing. You can look at the numbers this way, but there's power in that. Okay? If I'm giving you a quick presentation, I'm showing you stuff as a researcher. You might have a colleague presenting something. You know that there's variation associated with that data because you know how hard it is to get that data. For example, your colleague just gives you stuff like this, and you're thinking, no, I'd like to see. I know that there's a tendency for there to be variation associated with these data points in this particular field that we're discussing. What is it? Can you just give me a quick visual? So if you saw something like this for one of the data points, then you might say, okay, to whomever is giving the presentation, could I please take a look at that particular data point again? Or why is there such spread around about the tendency, the central tendency associated with that particular data point? And then you might want to dig deeper. Right? Okay, so that takes care of that. And I think, oh yeah, the next one is they're going to do percentiles. And that's percentiles and z-scores. Z-scores is very important. So median takes data and breaks it into, you find a median for data, you've taken the data and you've broken it in half, right? You do this box and whisker thing, you've taken the data and you've broken it into how many parts? 4. And if you deal with percentiles, you're taking the data and you're breaking it into 100 parts, right? So,
Sir, I have a question.
yeah,
For the boxing, like Whisker plot,
yeah.
like if we have numbers which are like 14 or 8, how can we find the like the range, like the interval range?
If you have numbers like 14 or
Yeah, like even like you have 14 data points or 8 or 10 or 12.
okay, you mean for the total?
Yeah, for the total. Like,
Okay,
how
so
can
so you mean if we had this? So if I did this and I threw away this,
we-
right?
yeah, like I know where the medians are, like the middle points, but like which points should I take and like find the interval like?
So at this point, we have 14 data points, right? So we're going to have 7 on one side and 7 on another. So 3, 4, 5. Whose music is that? 1, 2, 3, 4, 5, 6, 7. So we have a lower 7 and an upper 7. So we have to average these two, right? So actually, let's just make this more interesting. Let's make this an 8. Okay? So to get the median, in this case, is going to go right there, correct?
Yeah.
That's going to be 7 plus 8
and
over
then we
2.
take the average and we find the number. Yeah.
Now you can just go like this.
You got it.
Got it?
Yeah.
Okay. Break in half, break in half. Okay?
Yeah.
Okay? Okay, so I'm not going to spend too much time on percentiles because you know the idea now. But what we can do is we can quickly look at example 5. Let's do it pretty quickly. Okay, if you take a look at example 5, they give you a whole bunch of data, and I'm just going to count. It's 1, 2, 3, 4, 5, 6 rows by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. Okay? So you have 60 pieces of data. Now, conveniently, they put the data for this question on percentiles in 10 columns. Why do you think they put the data in 10 columns?
There are 10 different 10 numbers. 10, 20, 30, 40, 50, 60.
Because 10 times 10 equals what?
100.
Okay, so we have 1, 2, 10 columns of data, right? So it's going to make it easier for us to break stuff apart when we analyze the information. Okay, so if you take a look at, okay, so all of these apparently represent ratings based on sound quality, blah, blah, blah. The bottom line is that these numbers are supposed to, a high number means that these speakers that they're discussing are great, a low number means that the speakers are no good. If the audio maximizer scored at the 50th percentile, what was its raw score? So the question is, how do you find the 50th percentile? So where is the 50th percentile going to be? Yeah.
Fifth column, top, sixth column.
Ah, exactly. You've got to take this piece of information, and you've got to take this piece of information, and Alexei, what are you going to do with those two pieces of information? You're going to average them out. So what was this number here?
67.
And this question cost. This one is 67. And what was this one?
67.
67? Yeah? Okay, so in this case, it turns out that your answer is 67. Any questions on that? Okay, this is the lower half of the data. This is the upper half of the data. This represents the top end of the lower half. This represents the bottom end of the upper half. 50th percentile is going to be right down the middle. So what are you going to do? You're going to average these two. Just like the discussion we had with Guillermo a second ago about averaging these two, right? Exact same scenario. Average these two to find the center. You're going to average these two to find the center. Okay? Does this make sense so far? B, what is the 90th percentile for these data? Somebody want to take a stab at the 90th? Yes, sir.
89.
Can you help me out in terms of the visual on my board?
So the bottom one for the ninth column is the 88 and the top is 90.
The top of the 10th?
Yes. So I wrap them up. And,
There is a lot of water in here. Holy cow. Is there a leak here? Listen. What? You hear that? Where is this water coming from?
so this is a physics room now.
Is it?
I don't know. In the physics room there was a leak.
I don't see anything. Okay, so any questions on that? Cam, is that clear? Because your mouth is open. Is it?
I'm admiring the leak.
You're admiring the leak? Okay, me too. I don't see the leak. Does the Schmieder-Box's score of 75 place it at the 75th percentile? Well, where would the 75th percentile be? Aaron, what do you think? 75th. Where would 75th?
7th row.
Let me think about that. So the first row is anywhere from 0 to 10, right? So if you think about it, this is
Or the 8th row.
0 to 10. So this represents the top end. So if we go over here, right? Isn't this the 70 to 80th
Yeah.
right here? So isn't that the 70 to 80th? So that's, let me just write this, 70% to 80%. Agreed? You guys follow that? So they're asking for 75th, right? Which would be the middle of there, right? Now, how many data points are there per? Is it 6?
6.
So you've got 1, 2, 3, 4, 5, 6. Now, you have an even number of data points, right? So what are you gonna, you don't have an actual middle number there. So what are you gonna do?
Take the 2 whole numbers.
Right, so you're gonna average this guy, and you're gonna average this guy. Agreed? What's the top one here?
The top one,
That guy.
79.
And below it?
81.
81. And if we average those two, average is 80. And so that's the 75th percentile right there. And what's the score they're asking about? They're asking, does a score of 75 place it at the 75th percentile? And what is the answer?
No.
No. A score of 75 does not place it at the 75th percentile. Because the 75th percentile is a score of what? 80. Score of 75 is below that. That clear? You follow that, Darwin? 100%? Yeah.
So when you do part A or B, when you find the 19th or the 50th percentile, you don't care about how many slots there are. You just care about the end. And the
Exactly.
But if you find something in the middle, then you do care about.
Absolutely. Yeah. You're interpolating, right? You're interpolating. Well, and in this particular case, no, you have less than 100 data points, right? If you had 100 data points, or sorry, if you had over 100 data points, it's going to be a little bit different, but the idea behind it is the exact same. Just the number of parts you break stuff into. Okay, now this is very important. Okay, if you go to page 146, this is an important concept, and really, to me, it should be taught with probability distributions, but so be it. We'll teach it now because we're here. So I guess I'm going to end up jabbering a little bit about probability distributions for the sake of giving this context or rationale, but I'll try not to talk too much about it. Sorry, I really want to talk about. I'm just trying to think about what the best way to do this is. I don't know if I want to talk about standard deviations and all that stuff. Well, guess what? Okay. You know what? I'm just going to teach it in the context of the actual section, and I think it'll make sense to you, and then it'll have more. It'll have more meaning later on. Okay. Okay. A z-score is all about the number of standard deviations of data point is above or below the population or sample average. So, for example, you could have a bunch of data. Let's say for our population, your average is 50. I don't know what it is, 50 whatever, but let's say the average is 50. And let's say that it turns out that the standard deviation for that data is 1. Okay? If we're talking about a data point, let's say xi, let's say x47, the 47th data point has got a value of 51, okay? And maybe the 43rd data point has got a value of 51. How many, sorry, I'm going to make this 49. Take a look at data point 47. How many standard deviations? Sorry?
No, nothing.
How many standard deviations is this 47th data point away from the average? Agreed? Because standard deviation is 1. This is clearly 1 above 50.
Yes.
And how many standard deviations is this above the average? -1, right? It's -1 above, right? So, therefore, the general formula associated with these quite simply is as follows. For population, and then for sample of pop. And I think they still use the same letter Z for either case. For this one, it's going to be, well, for either one, the formula is the same, the characters are different. You're going to have your actual data point, right, which you'll call x, less the average. Suppose you could call it x sub I if you like. Doesn't matter. And you are dividing by what?
Deviation.
The standard deviation. In our case over here, for that 47th data point, we have a 51 minus 50 over 1, which gives you a 1 over 1, which is 1, which tells you the number of standard deviations that you are above the average. Okay? If you put in the 49th data point, you'd have 49 less 50, which is -1 over 1, which is -1, which means you're 1 standard deviation below the average. Now for sample, it's the exact same math. I checked the book, I still think they're using Z.
Yep.
Yes,
The only difference is that's going to become a number of standard deviations. Note, what are the units of this z-score going to be? What are the units of Z? Say that again? Louder?
There's no,
There are no units. Because let's say this was centimeters. Centimeters, centimeters, centimeters. Centimeter minus centimeter gives you centimeter, divided by centimeter gives you. So this is a unitless quantity, right? Unitless. So is there any value? What would be the value in that, in talking about stuff in this way? Bless you. You could conceivably have one study, okay, whereby, again, we're getting into distribution stuff. You could considerably have one study whereby you're talking about diameters, inner diameters of tires, right? Where the data tends to fall like this, okay? And you could be talking about another study where you're talking about mass of chocolate bars, you know, on a production line, where you have an average mass here and the data spreads like this. In both situations, you have a very similar spread of the data, right? But the standard deviation in one might be 6 centimeters for the tire diameter, and the other one it might be 1 gram for the actual chocolate bar. But in reality, they're very similar. Why are they very similar? Because in terms of the number of standard deviations, okay, a data point is relative to the average, they're the same. And so if you convert stuff into a z-score, you can compare apples to apples. In one case, you know, you're dealing with centimeters. In another case, you're dealing with grams and so on and so forth. Okay? So in terms of the shape of the probability distribution, one way to recognize that in fact these shapes are the same is to talk about the distance of data points from the average in terms of number of standard deviations. Okay? So it's a way of normalizing the data. It's a way of taking two different sets of data that have different meanings and converting that information into a standard that allows those two different sets of data to be compared to one another. Does that make sense? And it'll become a lot clearer when we go into actual probability distributions. Then it's going to become very, very, very clear. So I can ask a quick question. I mean, at this point it's like grade 5, right? There's not really anything here. So if I said population, so I could say here, the following is a sample. The following is a sample of data from the math scores on a class quiz. So I don't know. Just so nobody has a heart attack. That was out of 10. Okay. So, then I could ask you, and now we're going to have to, starting next class, I'm going to get the calculators, because this time I'll make you do it by hand, but after this time, you're going to use a calculator, just put in the data, and it'll give you all the information. I'll make you do it by hand just this once. So let's ask you a whole bunch of questions. So we'll say calculate. The data's mean, median, mode, standard deviation, variance, that's a good start. I can make this part A, and then I'm going to create a part B over here. I'm going to create a part B right over here. Create box and whisker and modify box and whisker plots for this data. And 2, what is the z-score of a quiz result of 8? Is that clear? Okay, so again, I'm keeping the data small here, the quantity small, because you guys are doing this by hand. What's going to be the most annoying part of this? Calculating what? Standard deviation is going to be the most annoying part. Again, though, once we take this thing up and we do it by hand, you're going to then use the graphing calculators, which we'll start with next week. Now, where's your biggest chance to make a mistake here? Where's your big opportunity to make a mistake? Where can you foresee a screw up? Right up.
Because it is sample.
Yes.
Sample standard deviation. You might like miss the -1.
Right. So you can screw everything up for parts A, 4, and 5, and conversely for B, 2, if you use the wrong formula for standard deviation, because as we've discussed in detail, there are 2 options there, right? In this particular one, Ilya, are we dealing with the entire class's test scores or just a bunch of them, a sample of them? Read the question. The following is a sample of data from the master one. So there may have been like 30 scores, right? There may have been 30 scores. But I've only grabbed randomly 1, 2, 3, 4, 5, 6 of those scores. So when it comes to your standard deviation or your variance formula, what is the denominator underneath that radical going to be? N minus 1, right? Correct. You're going to be using that version. And again, you're using that version because really, one of you slept in and got 0, and then the other one of you cheated and stole the answers and got challenged. But of course, did I grab those 2 data points in when I only grabbed my 6 data points? No, because the probability was low. There was a good likelihood that I would miss those outliers. And so as a result, your standard deviation gets tight, artificially so you have that denominator of n minus 1 to inflate it, to make it more representative of reality, which does have these outliers. And again, remember, based on the formula of standard deviation, do outliers have more of a quantitative contribution to the final number or less, and why?
More.
Why?
Because the distance is large, and then you have to like square it.
Perfect. Perfect. Not only, oh nice, Mr. Oh, that's just beautiful. Not only is the distance large, you're squaring it too, right? You're squaring that distance. So the outliers have the biggest quantitative contribution to the result. So if you're missing those in a sample, your number is really going to be low relative to reality. So the -1 kind of artificially brings us close to reality. Now why is it a 1, not a 2.7? I have no idea. Or a 12? No idea. Yeah. Variance.
Okay.
You weren't here?
Yes, sir.
Who's done? Who started? We have like 5 minutes. We should be able to get.
Five.
Do you guys want me to start on the board at the same time, or do you want to just do it on your own?
Do we? I'm gonna check it on Friday. Today's Friday.
On Friday? Today is Friday. Aaron, what do you think? You following?
Yeah.
Cool. So then, Yunjin, what do you think? We do take it up today or just on Monday?
I think today.
So we can do it.
Want to take it up right now? Okay, so maybe I should start. I'll start quietly over here, make myself a little home.
Yeah, I'm done, sir.
Good job. So Milad, can you give me the data in order, please? From lowest to highest?
For most,
From smallest to
4, 6, 7, 8, 8, 9. You mean the answer?
Why am I using X bar as a symbol and not mu?
Because it's a sample.
Milad, what is that?
7.
Clean?
Yeah.
Yeah. 7. Agreed.
Sometimes you can have more than one number being a mode, right? Let's say I had double 8, double 6, and no triples or higher. Then you can have more than one mode. What's next?
Standard deviation.
Oh god. This is going to be disgusting. I'm using the letter S, not sigma, right? Yikes. This is not going to be fun. I'm not looking forward to this.
5.
I'm going to have to write like a mouse.
Mira, do you get like 1.79?
Get 4 over root.
I got 1.788,
I get 1.79.
which is
Yeah.
yeah.
Oh, Mira, you are wrong. 100.
It's so sweet the way you said that. It's just, no, you are wrong.
Divide 4 by root 5 and 6.
I get 1.7888.
Yeah.
Instead of doing this, I could have just put a times 2, right? Because there are a couple of these.
Yeah, I get this thing.
Oh my goodness, this is awful. Just awful. Is that- I'm writing it all out just so that. Please double check my math. 10 and 6.
10 PW.
Does that look right? Please tell me it's right.
Yeah, it's right.
Somebody, can somebody crunch it for me?
It's 1.78.
1 point.
You know, and I'm gonna take more information. Then I'm gonna take a lot. You know why? Because then I'm gonna ask for the variance, and to get the variance, what do I have to do? Square it, right? So you were here. So give me like 4 decimals. So what does it come out to be?
1.7888.
Oh, is it repeating?
No, it's
No,
not
no,
repeating,
no.
that is one number left.
1.7888.
8.
Okay. So shoot, I have no idea here.
Root is 4 over root is 5. What's this thing?
It's not, it's 16.
It's the same thing.
4
Oh.
over root.
What's next? 5?
Variance.
minus square.
Now this is gonna be,
16 over 5.
this is, you know, so what would have, that was stupid. The way I asked it, what should have I asked for first?
Variance.
It would have been better if I asked for variance first, right?
Yeah.
It would have been cleaner, but now I'm gonna square this back. What does that give me?
3.2.
Yep.
You don't have to approximate that. It's exactly 3.2.
Oh, it was exactly? Okay.
It's closest.
What's next?
Do that.
So,
No, part B.
Part B, create.
Square whisker. Whisker.
The, how much time we have? 5 more, or do we have 5 minutes?
No.
No?
Yes, 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 yes.
Yes or no?
Okay, where is B?
Yeah.
Okay. 4, 6, 7, 8, 8, 9, right? We have 6 data points, so we have to average these two, right?
7.5.
So this is going to be Q, we can call this the median, which is also equal to Q2, which is 7.5. We got to go down here, right? Which is what?
Q1. Q1.
And we got to go down here, which is going to give us Q3, which is 8. So we go from 6 to 8. The middle is 7.5. 7.5 is closer to there. I'll do that. What is that? 4? 4. It's like 3.5. Then whatever. 7.5 to 9. So that was what was that? B1.
No, it was B11.
Oh right, like this is the box and whisker.
Yeah.
Now we have to check the modified.
It's the same.
I can tell it's going to be the same because the data is tight, but just to double check, Q3 minus, this is Q1, Q2, sorry,
It's within 3 of them.
Q1, Q2, Q3. Q3 minus Q1
8 minus 6.
is 8 less 6, which is 2. If you take 2 and you multiply it by 1.5, you get 3.
no,
What's 8 and 3? So you can see, well, we'll do both. Q1 minus 3 is 6 minus 3, which is 3. Any data points at 3 or below? No. We can check Q3 plus 3. What is Q3? 8, and 3 is 11. Any data points at 11 or greater? No. So modified B and W is same. We're almost done. And what's the last thing? The Z-score. It's nomenclature. I'm going to use that one. Z is going to be equal to, ask for a Z-score of a thing that got 8.
8 minus 7.
What is the average?
7.
What is the standard deviation? And what does that come out to?
0.55.
Sorry?
No,
Does it round to 5?
no, it's supposed to be round to 6.
Okay. Does that make sense?
So how much the bottom?
Now, having said all this,
So it's not 8.
having said all this, you're not going to be doing this by hand anymore, okay? You're going to be starting next week. You're just going to enter the data. But you're going to have to make sure that, for example, when you look at standard deviation, you take the right one because it's going to give you 2. One for, one for, right.
Sir?
Yeah.
So is this like typical questions that are
Oh yeah.